to induce seismicity and casing deformation. To start and frame the problem a little bit, when we talk about hydraulic fracturing, really what we're doing at the core of it is we're putting energy into a highly complex system. Of course, in the physical sense, we have a lot of inputs such as fluid, proppant, chemicals, diverters. But beyond that, we also have the energy or the horsepower on surface provided by these large pumps, as well as time and money that we put into this. And the product of this is hydrocarbons and hopefully a return on investment. However, this subsurface system is not simple. We have things like natural fractures, pre-existing faults. We have bedding planes that may serve as slip surfaces. We can have induced seismicity on these pre-existing faults, and we can also have things like casing deformation, where the subsurface moves in a way that causes our casing to be constrained, constricted, or in the worst case, actually broken. And in these cases, these can have operational impacts beyond just nuisance factors. Essentially, we can cause severe enough damage to our well infrastructure in the subsurface that we may need to essentially stop completions completely. We may damage wells and make them unable to come back online. And we may cause issues where we cannot get tools such as perforation guns or plugs down the well, and we have to leave some of our reservoir intact and we're unable to complete it. Beyond that, there's smaller implications of this. We can have stress shadowing as a result of these complex subsurface structures. We can have depletion from offset wells. This can cause things like asymmetrical fracture growth and fracture-driven interactions. This is primarily driven by processes such as geological heterogeneity. Essentially, within that subsurface, we have material properties that vary differently depending on their location. So this can be different layers that have different mechanical properties. And this can, again, be that presence of pre-existing faults or fractures causing issues. And so from a diagnostic and measurement technology perspective, there's many different ways that we can analyze the subsurface and try to get a better understanding of what's going on and try to help us plan and execute differently to mitigate these. So, of course, we've got things like temporary fiber or distributed acoustic sensing techniques, surface arrays or downhole geophone arrays. But in many cases, a lot of these are a post process. So we don't get that data in real time. And that can impact our ability to actually implement mitigation strategies as we're doing our completions. An example of this is if we only get an idea of where a fault is or when it's active, and once a pad is complete and that data has been processed, there's no way during that completions activity to identify that a fault has become active and to change our strategy in real time. So the question stands how we're actually able to mitigate these negative factors, how we're able to actually identify this, how we're able to change this perspective from a single completions where we set up a plan, we execute that plan, we analyze the results, and we iterate at the end. So the primary approach that we've taken here from a more holistic perspective is that rather than looking at each of our wells in isolation or each of our pads in isolation, what we're actually doing here is looking at our reservoir as a complete system. And within this system, we have stages that are completed throughout time, and each of those stages has an impact on our reservoir as that completions progresses. This shifts us from essentially a well-focused approach to what we would call a systems-based approach, where we're measuring the inputs to this system and we're recording the outputs or how that system progresses through time. The key idea here is that we're causing cumulative changes to the reservoir as our completions progresses. So it's not so much that a fault suddenly becomes active and starts causing issues. It's that we're constantly injecting fluid, we're constantly changing our stress states, And each of these subsequent stages causes additional and cumulative changes to the system as we go. This iterative process affects how we get the resultant deformation, which can cause things or induce things like seismicity or casing deformation on our wellbores. So the key here is we want to be able to track the temporal evolution of this process and understand how the system is responding to these cumulative changes in the reservoir. To do this, we do a combination of stress state metrics and energy metrics. At the simplest level, a stress state metric would be something akin to an ISIP or an understanding of the pressure response within the system as we complete. But within this, if we look at our individual stage, we can break down the amount of energy or the transition in energy between these stress states. What this allows us to do is understand and separate in real time how the system is responding during our completions, rather than needing to wait and evaluate at the end of a stage with something like ISIP. And so with this, we can transform an individual stage from a single discrete value to a continuous lens where we can see how the reservoir is responding as that completions progresses. And we can get an idea of how the cumulative changes to the system are impacting the deformation and energy release processes within the subsurface. And of course, the goal here is to be able to iterate faster and actually make changes in real time during our completions, such that we can implement mitigation strategies and techniques as those completions progress, rather than waiting to the end of the stage, such that we only know when that pad is complete and we only are able to make changes for the next pad on. This will give us immediate feedback. So this real-time data processing enables that during execution. Of course, it shortens the cycle where we can analyze and iterate and make changes, but not just make those changes, but actually evaluate what impact those changes have during our actual completions. This is more of a continuous feedback loop where we're able to make quick and data-driven decisions rather than trying to plan and implement on the subsequent pads. And the goal here is, of course, boosted return on investment, where we're stopping these nuisances before they arrive. We're mitigating, preventing damage to our infrastructure, and avoiding these costly interventions. So to get a bit more in detail on how this actually works, the way that Richter Predictor works is we analyze our surface pressure signal using high frequency and high resolution pressure gauges at the wellhead. The way that we consider this is that our surface pressure essentially acts as a distributed fluid antenna into our subsurface. So we have our pressure sensor at the top of the well, and there are acoustic signals that are within this pressure. And those acoustic signals can be analyzed and extracted in a way similar to how seismic processing is done. And with that, we're able to identify what we call resonant signatures. So on the right-hand side here, I have a spectrogram. If you're not familiar with a spectrogram, it's essentially a frequency and time representation. So we've taken our pressure signal, we've broken it down into the various frequency components, and the brightness here represents the amount of energy at a specific frequency. We can see through time here, this is approximately 3 hours or 3 stages in this case. We can see that there are resonant signals that appear. So we have this high concentration of energy. And as we change our completions, we can see that those resonant behaviors change. And so we're able to analyze, extract, and understand how these energy signatures change, how the acoustic response of our pressure is changing. And we can use that to infer subsurface deformation. To go into a bit of the background concept between this, we think of induced seismicity and casing deformation, along with fracture-driven interactions, as more of a sliding scale. So in the top left here, we can imagine our standard hydraulic fracturing operations. We're getting maybe regular bi-wing fractures or more localized fracture networks around our wellbores. We can start to measure things like fracture-driven interactions by monitoring offset wells to the well that's actively completing a stage. We can see that there are sometimes pressure spikes or interactions with these offset wells. What this can indicate is that we're forming larger, less complex, more planar fractures that are allowing pressure to be transferred within the subsurface to these neighboring wells. In very severe cases, we can see that these fracture planes essentially coalesce or combine. We have these large planar fractures that are concentrated on pre-existing fractures, on fault networks, or on weaker bedding planes. When this starts to occur, what we see is the process of aseismic slip, which often precedes actual induced seismic events. This aseismic slip also has the tendency to cause casing deformation, especially in areas where the wellbore passes through whatever plane is deforming. So you can imagine, for example, if you have the interface between two layers or two formations, as you frack, if that plane starts to deform and the verticals of your wells pass through that plane, you will see deformation along that plane where it intersects with those wellbores. And so from that perspective, we can see that all of these are caused essentially by the presence of larger, less complex, and more planar fractures, which are prone to this deformation process. And when this deformation occurs, it directly increases our risk of induced seismic events on nearby faults, as well as casing deformation in areas where those planes intersect our wellbores. So in terms of how we can actually measure this, again, what we've talked about previously is being able to break down our pressure into these frequency components. But at a micro level, essentially what we're looking at is these small fluctuations in pressure that occur during completions. And we can break this out into the frequency and the magnitude of these small pressure events. And we can extract those, focusing solely on these resonant signatures, and we can essentially add up the amount of energy or the amount of pressure fluctuation that's occurring within those signals. This gives us a base metric, which we call the energy density, and this represents the magnitude or the amount of energy within those resonant bands as the signal progresses. So this is essentially at the same sampling frequency as your source signal. We also produce a stage level metric, which is the derivative energy. And you can think of that as essentially taking a full stage worth of this energy release and normalizing it to the duration of the stage. And that way, we don't have stages which are perhaps a little longer, showing up as anomalously higher amounts of energies. And we can start to normalize that out. We can also do a cumulative metric where we just simply add up the amount of energy released within that stage. And so now looking at a case study here, this is a case study from the Montney Formation within British Columbia. And in this case study, we're looking at casing deformation. As I alluded to earlier, we have cases of casing deformation occurring at the interface between two formations, in this case, the Montney and the overlying formation, specifically where those verticals of those wells pass through that interface. And we know for a fact that this is bedding plane slip. It's been validated using caliper logs. There are INSAR studies that have been done to track the surface deformation. And we know that these are large horizontal slip planes that are essentially regionally continuous. And so I have here in the bottom right, the derivative energy across several of these wells as completions progresses. We can see here there are some earlier spikes in this derivative energy. So some wells will see a few stages where there's a larger energy release than typical. But across this 2 to 3 weeks completion schedule, we can see that there's a distinct spike here towards the end. And this spike occurs across all of our wells. So if we think back to what I was saying earlier about this cumulative deformation process and this understanding of the reservoir as a system, we can see here that there's a unique type of response that's occurring where all of our wells in tandem are showing this larger than typical energy release. And this did correlate to some stress state changes that were measured in post. The severity of casing deformation on this particular pad was severe enough that they had to leave a considerable amount of stages in the ground. And critically, there was no indication of deformation using their traditional seismic techniques. So they had a surface array that was being monitored during completions, and there was no large-scale deformation detected or no large events detected during this completions behavior. However, they ran caliper logs across their wells across various stages, and we could see that there was this evolving um, deformation that was occurring across the verticals, across the pad during this high energy release. So we have direct confirmation from those caliper logs that the amount of deformation occurring increased during this high energy period. But of course, it's not enough to just have a single pad and make a claim that we can detect this casing deformation. We did several pads with this client, and what we were able to see is that this is a consistent behavior across their formation. Once we got this initial signal and we were able to understand that it was occurring, we collaborated with them to implement interstage mitigation strategies. These are things that affect your frac order, for example, your stage spacing, your pumping duration. This could look like leaving one well behind and allowing other wells to get ahead. This could look like adjusting a zipper order, and this could look like cutting stages shorter or spacing them out a little further. And so from that first pad, we took those learnings and we applied those on the second pad. And we can see here that in the second pad, there is an increase in this derivative energy. And there was some of these mitigation strategies trialed here. During this trial, we were able to see that we essentially reduced the amount of energy that was being released. And beyond that, the amount of casing deformation that was recorded from their caliper logs was generally reduced compared to the first pad. Of course, one of the impacts of this is if you have to change your stage spacing or your pumping time, there's a balance there between leaving some of that reservoir in the ground in an effort to mitigate these casing deformation behaviors. In the third pad, they trialed a few more aggressive techniques. You can see each of these dots here essentially is when those stages are completed. We can see that we started having higher energy behavior across a few wells, and you can see there's a bit of a gap here. So essentially pausing those completions to try to let the system relax a little and reduce the impact of that deformation. And this was successful in that on this pad, we had very little deformation relative to the other ones. So we can see here the direct application of identifying when there's high energy release across various wells, using that to inform strategies in real time rather than as a post-pad analysis, and implementing that in a way that produces verifiable and reduced impacts of casing deformation. Beyond that, we've also applied this to induced seismicity cases. So again, if we think back to the actual process here, when we're talking about casing deformation, induced seismicity, and even fracture-driven interactions, what we're really looking at is the coalescence and the simplification of our fracture network along these larger planar features. In this case, we're looking at a two-pad well within the Duvernay Formation, and these wells were located in a strike-slip stress environment with multiple offset structures. You can see a simplified view of the pad here where we have these structures. There was another structure towards the toe, but we're focusing on the structures that are directly offsetting the well. And so as completions progressed, we did see from their surface array the activation of these various fault structures offsetting the well. And as this completions progressed, we also noted that there was high energy stages towards the heels of these wells. The largest event that was detected was a magnitude 3.01 local, approximately 200 meters from the wellbore. And the energy that we measured indicated that the stages prior to this fault interaction were prior to this large event. So here again, looking at our derivative energy, the units are different here as we're operating in kilopascals instead of megapascals. But what we see is, as we complete during these various other fault structures, we see some interaction especially with well B here, and this as it's closer to those fault structures. But critically, as we're approaching this final fault, which had the largest activation, you can see in the bottom right here, the individual events that were picked. We can see that just prior to this magnitude 3 event, which is just at the regulatory limit for this area, there was a very large energy spike that was completely anomalous based on everything we'd seen so far. And so we sent this operator a message essentially indicating that we detected this energy anomaly and there was a risk of a larger magnitude event as a result based on our interpretation. And this early warning was sent 1.5 hours before this magnitude 3 event occurred during their completions. And we can see after that event occurs, generally we reduce the overall amount of microseismic events on this fault structure. And in tandem, we see a reduction in our energy detected across those two wells. So from this, we can infer that we are directly seeing the impact of this deformation within our completions. We can assess the amount of energy that's being released, and we can tie that to detecting anomalies and sending early warnings when those anomalies are detected. Of course, this is highly dependent on each individual basin. The appropriate risks of casing deformation are not uniform. The appropriate risks of induced seismicity are not uniform. There's different stress states. There's different orientations of bedding planes and pre-existing fault structures. But in general, the trend that we've seen across these various different structural regimes is that we see these large releases of energy, and these acoustic signals from that can be detected within the pressure prior to casing deformation and induced seismicity occurring. I'll now briefly touch on one of our other case studies where we have direct comparison to microseismic, full waveform microseismic. In this case, this is essentially looking at a 3-component broadband seismometer. This is within the Permian Basin in Texas. And what we're able to see here is a magnitude 2 event which occurred relatively close to our wellhead. At the same time, we were recording a high frequency pressure gauge, and we were computing the energy density of this pressure gauge as our completions progressed. We collaborated with this operator to assess essentially when these events were occurring on this nearby fault structure. And what we were able to see is that when this event occurred, one of the larger events in the area, we were able to pick up a pressure fluctuation just prior to that event and continuing afterwards. And this aligned quite well with what we saw from this magnitude 2 event. Beyond that, we have a case study from the Montney Formation in British Columbia. This case study had full waveform geophones, about 200 geophones as a surface array. And we also had pressure gauges at this site during these completions. What we were able to do with this very dense surface array is we're able to perform a similar analysis as we do on the pressure on these geophones. What we were able to do is when we look at the frequency breakdown between, on the left-hand side, a geophone spectrogram. So this is produced directly from those full waveform geophones. And on the right-hand side, looking at the spectrogram from our pressure signal, so a pressure sensor on the surface, we can see that the resonant frequency bands between these two are analogous. And this validates that what we're seeing within our pressure is a true physical signal that is coming from the subsurface. This has been documented in various studies over the years, particularly those out of University of Calgary. And we've also been able to validate this with this raw data. We performed a polarity analysis of this, and we're able to show that these resonances are directly emanating from a primary fault structure. And this primary fault structure at the time had caused the largest induced seismic event from hydraulic fracturing in the world. This is a case study from 2015. And so what we can validate with this is our geophones are able to point us that this resonance is coming from the fault. We're able to do that polarity analysis. And we're also able to do our frequency analysis and validate that the frequencies that we're seeing in those geophones is the same frequencies that we're seeing within our pressure. And so we have justification that these strong resonances that we're extracting and understanding the energy of are directly tied to these subsurface deformation processes. Finally, to round this out, I want to touch a little bit on where we're taking this technology, where we're hoping to go with it. And one of the things that we've noted is that these resonances can be tied to various behaviors, both operationally. So in certain cases, when we adjust our rate or we adjust our propant, we can see changes in our resonances. We can see that we're affecting the amount of energy that's being released by the subsurface. And this goes beyond just casing deformation and induced seismicity. We have several case studies where we implement mitigation techniques in real time for the arresting of fracture-driven interactions, particularly within the Haynesville. We have a collaboration there that was, I believe, presented at HFTC. And in those cases, what we've seen is changes to rate or dropping of diverter or using a sand slug can be effective at mitigating fracture-driven interactions. And if we think back to, again, what we're discussing of this sliding scale, those fracture-driven interactions are indicative of larger scale planar fractures. And it's possible that some of those same mitigation techniques and learnings from fracture-driven interactions can be used as a way to try to divert our fractures from accessing these large planes, which increase our risk of casing deformation or induced seismicity. So from that, we can see as an example here, as we get our breakdown and we reach our maximum rate here, we can see that there's various resonances that initiate. And we can see throughout our completions, as we affect our rate and change how we're interacting with that fluid, we can arrest or reinitiate these resonances. And so a large area of our study now is rather than using interstage mitigation strategies, looking towards intra-stage. So within the stage, what changes can we make? What approaches can we try to actually arrest some of these high energy resonances, which are indicative of that deformation? And if we can develop those, then there's a clear strategy to implement these in real time and to prevent or arrest that casing deformation before it gets so severe that it impacts our subsurface. So essentially what we're looking at here is a combination of our energy metrics, as I discussed throughout this presentation, and our stress state metrics, which are things like our post-fracture pressure decay, as well as those FDI or offset monitoring techniques. And we can pull all of this together into a single system where we can start to give recommendations in real time based on how that system's actually reacting, rather than trying to assess everything at the end of a pad and make a better plan for the next one. In summary, what I presented here presents a new lens into behavior that's not often captured with most traditional techniques. It's non-invasive, so we're only looking at surface pressure gauges, and it allows for continuous deployment. It's supplemental to our existing methods, so we have strong integrations with microseismic providers, assessing that data as it comes in. And it helps us capture those energy transitions between stress states rather than focusing on post-stage analysis or post-pad analysis. And the critical thing here is this allows us to make changes in real time and to evaluate the impact of those changes in real time. With that, I'll say thank you and happy to answer any questions.
Well, thank you, Thomas. That was outstanding.
Thank you.
And We do have a few questions. The first is from Suresh, and he's interested in a little more details on how the energy derivative is computed.
Yes, yeah. I'll maybe pop back to, um, got an earlier slide here. So yes, this one. We have a proprietary analysis technique. Without giving away too much of the detail, essentially what we're doing is we're analyzing our high frequency and high resolution pressure gauge data. So we get that data streamed from the field, that data sent to the cloud, where we have our real-time analysis engine. That engine applies our algorithm, which is capable of extracting those various resonant frequencies. And with that extraction, we can look at the pressure magnitude of those individual fluctuations. So if you think back to high school physics classes or early university physics classes, wave superposition, essentially being able to add different frequencies together to make uh, a larger wave, we can break out those individual waves and understand how much pressure fluctuation is associated with each of them. It's akin to a filtering technique, but oftentimes filtering techniques throw away this information, whereas what we're interested in is actually extracting this information, breaking down those frequencies, understanding the behavior of those resonances through time, and essentially summing those up to get an idea of the energy release.
Excellent. Julian is interested in some of the details, the sample rate for your pressure sensor and typical resonant frequencies.
Absolutely. So, as a base level, we do have 1 hertz pressure sensors. Without going into maybe too much detail on the signal analysis side of things, the basic way I would describe this is that a 1 hertz pressure sensor can give you an idea of the strength, but you lose a lot of frequency resolution, obviously. Um, we do also implement, as more of a standard, 50 hertz pressure sensors for this type of analysis. And we have several case studies that are ongoing with clients with up to 1,000 hertz pressure sensors. As a typical, though, we have two main streams, one being those 1 hertz and the second being those 50 hertz. In regard to the typical resonant frequencies, um, I would say there is a broad range. Within our signals, we can see resonant frequencies anywhere in the very low frequency spectrum of sub 1 hertz, all the way up to 10 to 15 hertz for some of our um, more surface impacts. And beyond that, there are what we would refer to as harmonics that will be integer multiples of those lower frequencies, and those can go all the way up to 500, 800 hertz. But our main analysis is in that, I would say, sub 1 hertz to 25 hertz band.
Uh, uh, Thank you. Now, Alexei has three questions, one of them with sub-questions. And this, I think, is an important question. What is the physical explanation for resonance frequencies? What does the
Yes.
signal actually represent?
No, that is a fantastic question. I would say, to give a very brief background on um, what I would refer to as tremor signatures. Tremor signatures are something that has been detected across the geologic spectrum. Um, I'd be happy to talk about it on end as it's a large part of my PhD. But without, again, going into too much detail, we can see this across volcanoes, subduction regimes, even glacial ice movements, um, obviously subsurface deformation, fault movements, and hydraulic fracturing. Not just hydraulic fracturing with water as the fluid, but also CO2 injections have seen these. There's been studies where they have downhole geophones in offset wells directly next to the frac stages, and they can see these resonances developing. And the path effects of those have been discredited, and essentially it's a source effect near the active frac stage. So when we consider all of that, where we're seeing it in volcanoes and subduction zones, my interpretation of them is that they are uh, directly caused by that deformation process. So as that surface is slipping slowly or aseismically, it's generating a tremor signature, which we can then pick up through this hydraulic antenna, as I refer to it as.
Can you also talk about the SNR, the signal to noise ratio? Alexei's concern is that he anticipates that there'd be a fair bit of friction in the pipe and presumably in the fractures that would mask the relevant signals.
Absolutely. Yes. So one part of maybe I'll frame it a bit more of the where we are and where we're going. The where we are is we've detected very strong anomalous energy releases that directly correlate with these deformation processes. So again, to sort of frame that, um, there's a lot of complexity within these signals, especially when we start to move into these higher frequency signals. We can see patterns and start to break out individual components. We're learning more and understanding what is background noise and what is representative of these deformation processes. And within that, um, we're able to see that there are distinct signatures of these very high energy release processes that are different from the typical behavior that we see within a pressure signal. So the more advanced implementations that we've worked on essentially have a more of a intelligent filtering process to remove typical behaviors and focus purely on those highly anomalous behaviors.
And I think you've partially answered Alexei's third question, but does your technology just indicate that something is changing, or can it also suggest what and where so that really informed decisions can be made in real time?
Yes, again, great question. And I'll again frame it a bit of the what exists now and what the next step is. And what exists now is in the first regime, where we're understanding that something is changing and something is anomalous. What we've been focusing on, especially with these high frequency gauges, as well as integrations with microseismic technologies, is validating which of those behaviors are from particular types of fault structures. So I mentioned very briefly a bit on polarity analysis, but we've been in tandem with this developing techniques for processing microseismic data and using those microseismic data to get an idea of the where. So there is an integration that can be done there, not just to validate, but also to be used in tandem. Um, as a base, obviously, the pressure signal is not a spatial technique. We cannot get an idea of where around our wellbore without integrating either other wells through, for example, those fracture-driven interactions or offset measurements, or through integrations of other technologies such as geophones.
Okay, and then Trenton's question is similar to one of Alexei's questions, but maybe you could add on. And he enjoyed the talk, by the way. Is it necessary to filter out pressure signals from the pumps or any other surface equipment upstream of the wellhead pressure gauge?
Yes. As a basic level, yes. So a lot of our algorithm is focused on that aspect and essentially characterizing those different signals such that we have a better filter for understanding what's going on.
Um, okay, and John is wondering if there are any distinct seismic or aseismic representations of casing deformation itself occurring.
Yeah, so if I'm reading that, I would say very flatly, casing deformation does not always generate induced seismic events. Like full stop. Um, when we talk about that sliding scale, that's more of a conceptual tool to understand that those large planar structures are what are prone to deformation. Um, Beyond that, there's different types of seismic processes that can occur on these planes. We have many examples now of large scale horizontal bedding plane deformation with little to no observable microseismic events. So essentially silent to traditional techniques. But the implication of that is that we can have movement of the surface, which can impact nearby fault structures. So, and maybe I'll hop to this one. In this case study in particular, we're looking at horizontal slip plane, which caused interactions with a large fault structure that was 1.5 to 2 kilometers away from active completions. So we're dealing with um, deformation that's been validated through INSAR, and we're seeing that it's interacting with a fault structure and inducing a large seismic event, but it's not necessarily that every casing deformation or every bedding plane slip causes a large seismic event. That large seismic event occurred on a pre-existing thrust fault that was critically stressed, essentially, before completions. Hope that sort of clarifies that.
We have one more interesting question from Kai Ben, and his I'll try and paraphrase it. And he wants you to elaborate a little bit more on prediction of induced seismicity.
Yes, yeah.
Um, do you mean to say that the resonance you're measuring precedes actual substantial slip?
Yes, I will also clarify the name Richter Predictor. I have to give credit to my younger sister for coming up with such a catchy title. Um, but essentially, what we're looking at here is breaking out from our pressure signal an indication that there is a large release of energy that we are not expecting from the subsurface. So we're performing some action, we're putting fluid in the ground, and we expect to see this typical behavior. And in some cases, we start to see uh, unexpected behaviors, larger amounts of energy being released. And in terms of prediction, what we're looking at there is assessing the risk. And we've seen a strong correlation between large releases of energy and these detrimental casing deformation or induced seismic events. So, from that perspective, we're seeing that this energy release process, which is tied to the deformation, comes before um, these large scale slips, which can result in casing deformation or induced seismicity. So, from a risk perspective, if we're seeing this large energy release, and we know within this basin that there's a risk of casing deformation, it's been documented, or we know that there's nearby fault structures, that increases the risk that those um, deformations may occur on our well bores or that we may be interacting with those fault structures at a distance. Hope that clears that up.
And just to follow on that with the next final question, Julian is interested. whether the resonance frequency, sub-hertz to 25 hertz, whether that value indicates anything particular about the fault structure or the deformation behavior.
Yeah, that is a lovely question, and if you find out the answer, please let me know. No, in all seriousness, we have seen that most of the large scale deformation behavior is in the lower frequency bands. So, from our uh, case studies and the data we've been able to collect, these lower frequency bands are indicative of when these deformations are occurring, and these higher frequency bands are associated with our more typical fracturing behavior. So there is, I would say, some intuition there that smaller structures like our more typical fracture networks are higher frequency and these larger structures are lower frequency. It would align with what we've seen in literature from other environments. As I was mentioning, subduction zones are characteristically a very low frequency sort of tremor behavior. Um, but that being said, I'm sure there's a lot more nuance and a lot more learnings that we need to get to really understand um, if it means something in particular about the fault. But it is something that we see across geologic environments and particularly those lower frequencies.
Okay. Well, last call. Um, well, with that, Thomas, I really want to thank you for an excellent and very provocative and informative presentation. This was really cool. Thank you so much.
Thank you. And happy to have been able to make it. So thanks.